Hi, it's Mr. Duffy. Welcome to physics. Today our lesson is going to be about constant acceleration. So let's go ahead and get started. In our previous units or lessons, we've been talking about objects that have constant velocity. But we know that all objects do not move with constant velocity. They're not always moving the same speed throughout their whole motion. We know that things do speed up and slow down. And that's where we get into the term of acceleration. But specifically for this lesson, we're going to be talking about things that have a constant acceleration, an acceleration that's uniform. It's not changing throughout its motion. That makes it easier for us to analyze their motion. If the acceleration of an object was changing or varying as through its motion, then it'd be more difficult to analyze what it's doing. So let's just talk about first off what acceleration is in the first place. Basically, again, acceleration we can think of the rate at which velocity changes over time. Easier way to say something is if something's like speeding up or slowing down. But things can speed up quickly and things can slow down quickly. So again, it's the rate at which this happens, but it's a change in velocity, and acceleration measures that. So we have an equation to explain acceleration. It's the change in velocity, or you could do delta v over the change in time, which would be delta t. Remember that delta, the little triangle symbol, means change in. So the change in velocity over the change in time. I have the box with a abbreviated equation there. So a equals velocity final minus velocity initial over the change in time. Or again, you could have acceleration equals the change in velocity over the change in time to shorten it up even more. Now, when we talked about velocity, we talked about the units for velocity, which we'll normally use, which are meters per second. So given that the common unit for velocity is meters per second, the one that we're going to be using the most, the common unit for acceleration is going to be meters per second squared. Now, how do we get that? Again, if your units for velocity are not meters per second, then you're not going to get the units of meters per second squared for your units for acceleration. But most of the time, we are going to have meters per second as our velocity units. So again, if we're trying to figure out meters or acceleration, we can use the change in velocity. The change in velocity will have the units of meters per second, and we're dividing that by seconds. When you divide by something, you divide a fraction, basically it's like multiplying by 1 over that number. So if we're doing meters per second times 1 over seconds, you can see that gives us the final unit of meters per second squared, because seconds times seconds equals seconds squared. So that's how we end up with the unit for acceleration of meters per second squared for acceleration. Right, now let's take a look at a problem for acceleration using that equation. Here I've got a car that's moving down the road, and it says car is traveling with a velocity of 13 meters per second east, and the driver wants to pass a truck and speeds up to 19 meters per second. He does that in 2 seconds. What is the car's acceleration during that time period? So again, acceleration equals my change in velocity. My change in velocity, final minus initial, over the change in time. So it changes by 6 meters per second, and it does that in 2 seconds. So my acceleration is 3 meters per second squared. And one thing we kind of didn't talk about in the last slide was that acceleration is a vector quantity. So it has an amount. In fact, here also the amount comes out as positive. So again, that kind of gives us a clue as to what's going on. But it's moving to the east, so that would be our direction component to acceleration. So it's a 3 meters per second squared east would be our acceleration. So this brings into the next question. Hopefully a person's driving a motorcycle with a speed of 4.5 meters per second down the block. She turns right with a velocity of 4.5 meters per second and continues down the street. Did the driver accelerate? The answer to this is yes. Yes, the driver did. And like I said in the last slide, it's all because of acceleration being a vector component and having a direction that is associated with it. This motorcycle changed direction, so that motorcycle did accelerate. Okay, so again, acceleration is a vector quantity. One more question. The car is moving down the block 10 meters per second. It sees a stop sign and slows down and then stops in 4 seconds. What is the car's acceleration? So this is a great example of will end up being a negative acceleration. So again, acceleration is the change in velocity over the change in time. The final velocity, it doesn't really say it specifically, but it says the car comes to a stop. We should know that that means a final velocity of 0. So 0 minus the initial velocity, which is 10 meters per second, over the change in time of 4. So then that would equal negative 10 over 4, which would come out to negative 2.5 meters per second squared. Now, this one, again, we don't necessarily know what direction it was going in the first place. But we do know that it still would be considered a vector quantity, though, because the negative sign. The negative sign tells us that basically it's in the opposite direction of its motion. So whatever that was, whatever way it was moving, it's moving in an opposite direction. The acceleration is in the opposite direction of that the car's velocity. Which brings us into a chart that I like to show. We can tell a lot about an object's motion by looking at its velocity and its acceleration. We can tell what the object is doing if we again know its velocity and we know its acceleration values. Again, the positive and negatives that go along with that, because we're just talking about one-dimensional motion. So this table again kind of sums up if the cars or the objects can be speeding up, slowing down, so forth, moving at a constant velocity. And again, it all depends on the sign of the velocities and the acceleration. If velocity and acceleration are both positive, the car is going to be speeding up. If the velocity and accelerations are both negative, a lot of times we would think, okay, that's slowing down. But actually, that is still speeding up. It's just speeding up in the negative direction. It could be speeding up as it's going down, or it could be speeding up as it's going to the left. It's when the signs are opposite of each other, that's when it's slowing down. So if the velocity is positive, the acceleration is negative, that object would be slowing down. But if the velocity is negative, the acceleration is positive, that object again would be slowing down. So if the signs of acceleration and velocity are the same, speeding up. If they are opposite each other, slowing down. If the velocity is positive or negative, it doesn't matter, but the acceleration is 0, well, that would mean the object is going to just continue doing what it's doing and moving at a constant velocity. It starts with 0 velocity and has a positive or negative acceleration. That means it started at rest, it was at rest, and then it is speeding up from there. Finally, if both the velocity and the acceleration are 0, then it's just staying at rest, not doing anything. So I think this, again, is a very useful table. Kind of, again, sometimes we have trouble thinking about positives and negatives and the direction component of velocities and accelerations. But again, with this information, we can kind of analyze what an object would be doing. Let's take a look at a special case for acceleration. I want you to ponder, an apple falls from a tree. Is it accelerating? I mean, a lot of the times, this came up on our first, is it moving? We talked about that in the first lesson. Yes, it's moving because it changes position, but is it accelerating? So as you think about that, I think you should ask yourself 2 questions. Would you catch the apple if it dropped from the top of the tree? Okay. If I drop the apple from the top of the building, 10 stories up, would I catch it? And I think for your first answer, you'll probably say, yeah, I would catch that. And I think you might be a little bit more hesitant on the second one. And the answer is why. I mean, if you're questioning that you would catch it on the second one, then your answer should be yes, it was accelerating. It's going a lot faster after it falls off a 10-story building. And so that means the object is accelerating. Sometimes it's hard for us to think about accelerating objects over a short distance. A lot of the times we think, again, if it's just falling from a tree, we wouldn't necessarily think it's accelerating, but it does. It just doesn't have as much time to speed up. If an object's falling for a longer time period, it has a lot longer to speed up and a lot longer to, it's going to be moving a lot faster when it actually reaches you. So if you're having trouble thinking if is something accelerating, think if I, had a longer time period, would I catch it, or something like that? Then, that would bring you to the acceleration answer. What is causing the acceleration in this case is special. Gravity is actually causing this object to accelerate. And gravity has a constant acceleration of negative 9.81 meters per second squared. And it's constant. So again, that's why we're kind of talking about it in this lesson. But also, one of the things you should notice is it's negative as well. Negative is just indicating the direction. So a lot of times, again, direction just means down. In this case, negative means down. Um, so again, that's if you drop an object, it's moving at a constant acceleration of negative 9.8 meters per second squared. But again, the negative is really just indicating down. Now, gravity is a force, and we will come back to this a little bit in a later unit. But again, it is causing a constant acceleration. So I want you to be aware of it now. When motion is falling under only the influence of gravity, we call that free fall. Free fall is the term for objects falling under only the influence of gravity. Now, I have a picture of skydivers. I'll come back to this here in a bit. They aren't necessarily only falling under the influence of gravity, but again, something that's falling under the influence of gravity, we would consider in free fall. Here's what an object falling in free fall would kind of look like. And I think this picture really does a good job of illustrating how the object's moving. What it is a strobe photograph. It's a photograph that's taken at regular intervals with 0.1 second intervals between each of the pictures. So you can see the ball starts at the top. It's dropped out of this tube. And then every 0.1 seconds, the picture is taken. And what we can notice as the ball moves down is that there is an increase in distance between the balls. The balls are moving further in each time frame. Now, we're going to look at position time graphs with acceleration in them in a later lesson. But again, I want you to kind of think about what that would look like on a position time graph, and we'll analyze that a little bit later. But again, we can notice that this object is accelerating under the influence of gravity because the distances are increasing. I want to come back to only gravity can be causing the acceleration. So free falling objects, when we say free fall, we mean only under the influence of gravity. And when objects fall with only the influence of gravity, they fall at the same rate. Here I have a picture of an apple being dropped and a feather being dropped. But the special situation here is that this is being done in a vacuum chamber. There's only gravity. There is no air to affect the fall of the objects. So they fall at the same rate. We a lot of the times think, different objects fall at different rates, and that's because there's air resistance normally in our everyday lives. The skydiver, again, example is there is air resistance, and air resistance is a force. Again, we'll come back to that later in a later chapter when we talk about forces. But for free fall, we're assuming that there is no air resistance and all objects will fall at the same rate. There are very cool videos about objects falling in vacuum chambers at the same rate. I would encourage you to go watch one of those. They're pretty neat. So air resistance, I'll leave you with this. This is our last slide. Air resistance is a force that causes and pushes up against objects that are in free fall. But we are going to ignore this for this unit. When objects are in free fall in this chapter, we're going to say that there is no air resistance at all. Only gravity is actually affecting the motion of the object. But that is not the truth in real life. And we will learn in a later chapter how to compensate for that. So hopefully after this video, it makes a little bit more sense what acceleration is and how to calculate it. Also to how to analyze the motion of an object if you have the velocity and the acceleration quantities. So thank you for watching.